Okay, let's unpack this foundational idea. If you're just starting to explore the world of generative AI and thinking about building something, anything at all with these powerful large language models, you might feel a little, well, like you're standing at the base of a mountain.
Uh-huh.
So many concepts, so many different frameworks and possibilities. It's easy to look up and think, where do I even begin to build something useful with all of this? It can feel incredibly overwhelming.
Oh, absolutely. That feeling is completely understandable and frankly very common. I mean, the capabilities are vast and the terminology alone can be, well, it can be a barrier, right?
Yeah.
Trying to conceive of and build a complex multi-turn conversational agent or, a sophisticated system that chains multiple AI calls right out of the gate, that's like trying to climb the entire mountain in a single leap. It's probably going to lead to frustration.
Agreed. So what's the antidote to that initial overwhelm? How do you, like, find the starting line for building?
The elegant and I think highly effective answer lies in embracing simplicity first. Before you attempt that complex multi-step system, you really need to truly understand and master the single perfect interaction.
Okay.
You need to start with the most fundamental kind of atomic building block of an AI agent.
And that brings us directly to the core concept we're diving into today. We have a fantastic set of lecture notes here from Jaewa Choi, an associate professor at George Washington University, associated with the CAFA initiative. And these notes, they lay out a specific foundational model for this essential starting point.
That's right. The model they present, which really serves as the absolute bedrock for understanding AI agents, is called STAR.
STAR.
And STAR stands for Single-Turn Agent Replicator.
STAR. It sounds like the first point of light you see when you look at the night sky. A starting point. Right.
It's intended to be exactly that, your starting point, the fundamental unit. Our mission for this deep dive is to unpack these notes thoroughly. We want to help you understand precisely what the STAR model is, break down how its simple structure actually works under the hood, explore why this seemingly basic idea is not just important, but the absolutely crucial first step if you aspire to build any kind of AI agent, no matter how complex it might eventually become. We're going to have a deep, detailed look at this foundation.
Fantastic. So let's jump right in then. You mentioned the core problem is that initial confusion when trying to build. How does understanding what a single-turn agent is, and specifically this STAR model, how does that solve it?
Well, the main barrier isn't just the complexity of the AI models themselves, the LLMs. It's often figuring out how to structure an application around them.
Right.
How do you reliably get information into the AI, process it correctly, and get a useful result out? The philosophy behind starting with a single-turn agent is basically to strip away all the complexity of memory, conversation history, multi-step workflows, all that stuff.
Okay.
And just reduce the problem to its absolute minimum. You learn to make one perfect, self-contained exchange happen reliably.
Okay. It's like learning to pass a ball perfectly every single time before you try to coordinate, like passes across the whole field in a full match.
Exactly that. A perfect analogy. And the STAR model is the formalized definition of that perfect, isolated exchange. At its core, a STAR agent is designed to process one single user request at a time.
One request.
Just one. It takes that request, does its designated internal processing work based on its instructions, and then generates and delivers a single direct response.
Okay. And a critical descriptor used in the notes is stateless. That sounds important.
Yeah.
In the context of AI agents, what does stateless fundamentally mean?
Yeah, stateless is key here. It means the agent retains absolutely no memory or context from any interaction that happened before the current single request it's processing.
Not at all.
Zero. Each interaction is completely independent and isolated. You can think of it like interacting with a vending machine. You put in your selection, that's the input. It processes that single request and gives you your item, the output. And then it's just ready for the next customer's selection with no memory of what you just bought.
Okay.
If you interact with it again, even a second later, it treats you as a brand new customer with a brand new request. There's no session history, no continuity from one turn to the next. It just doesn't remember.
Okay, so it's the purest possible form of an input process output machine. It takes one specific input right now, does its thing based only on that input and its internal rules for this single turn, and gives one specific output.
That's precisely it. It embodies that fundamental computational concept, input, processing, output, in its most direct and transparent form. And this deliberate simplicity, well, it offers enormous advantages, especially when you're learning or building foundational tools.
What kind of advantages?
Well, firstly, it makes the model highly predictable. Because it doesn't carry history, you know that the output will be solely determined by the current input and the agent's fixed internal logic for this turn. If you provide the exact same input again, you should theoretically get the exact same output, assuming the underlying LLM is consistent, of course.
Right, less variability.
Exactly. And secondly, it makes it very efficient. There's no need to store, manage, or retrieve complex conversation history. That simplifies development quite a bit and reduces computational overhead.
So simplicity leads to predictability and efficiency. Okay, that makes sense. But this isn't just about building tiny, isolated tools, is it? You said it's the building block.
It truly is the fundamental building block. The lecture notes really emphasizes this as a core takeaway. Mastering this single self-contained exchange is not just some academic exercise. It's essential because when you graduate to building more sophisticated systems, agents that do maintain memory across multiple turns or complex workflows involving multiple steps or even multiple agents collaborating, you are almost always building by sort of stringing together, orchestrating, or calling many of these core star interactions. You perfect the fundamental unit, first the single brick, let's say, and then you learn how to combine those bricks to build walls, rooms, and ultimately the entire structure. You can't really build a multi-story building without mastering how to lay a single, stable foundation unit.
Right, that makes intuitive sense.
Yeah.
You build proficiency at the lowest level of complexity because that skill translates directly to higher levels. Okay, so let's visualize this. The notes include a schematic, a diagram showing the flow. Can you walk us through exactly how this input process output looks step by step within the STAR model?
Absolutely. The diagram is beautifully simple and linear, which really illustrates that one-way path we discussed. Imagine a vertical flow, kind of top-down.
Okay, I'm picturing it.
Yeah.
A top-down diagram. Straight line.
Step 1, right at the very top, is the greeting. This is the agent's initial interaction with you, the user. It's the point where the agent introduces itself, presents its purpose, maybe provides instructions, or perhaps shows a menu of options. It's the agent setting the context and initiating the exchange.
Got it. The agent says something like, "Hello, I am a lesson plan generator. Please tell me about your course." Or, "Welcome to the grading assistant. Please provide the student's work." Something like that.
Exactly. It's the agent establishing the parameters, the rules of engagement for the upcoming interaction. Then, flowing down from the greeting is step 2, user input. This is where you, the user, respond to that greeting. You provide your specific request, your data, your question, or maybe select an option from the menu it presented. It's your contribution to the single turn.
So the agent prompts, the user responds. Okay, this feels like the setup for the core work, the main part.
Precisely. Now, below user input in the diagram is step 3, labeled internal processing. This box represents the hidden logic of the agent. And crucially, it shows the system prompt combining with the user input. This is where the agent's predefined instructions meet the user's specific request for this particular turn.
Okay, hang on. The system prompt, that's those hidden instructions the developer wrote, right? Defining the agent's identity and task.
Yes, absolutely. Think of the system prompt as the fundamental rules and purpose given to the agent by its creator. Things like, you are a helpful assistant, or your goal is to generate creative writing prompts, or maybe analyze the following text for sentiment. These standing instructions are fused, combined with the specific message or data you, the user, just provided in your input.
So the agent's general rules for existence, its core programming, let's say, meet the user's specific command right now. They merge together.
That's the perfect way to put it. They fuse together, and they form a complete, highly specific instruction or task for the large language model. That combined instruction is what's sent to the LLM in step 4, LLM processing.
Right.
This is where the powerful AI brain receives that complete contextualized prompt, the system prompt plus the user input, and performs its generative or analytical work based on its training data and those specific instructions it just got.
The LLM takes the blended instruction, figures out the best response based on everything it knows and the rules it was just given.
And finally, flowing out of the LLM processing is step 5, output. This is the result generated by the LLM, formatted and delivered back to you, the user. It's the agent's final answer for this turn, the generated content, the analysis, or whatever the specific task was.
So it's a very clear linear path, greeting, user input, out internal processing, and that's where system prompt plus user input combine, then main LLM processing, acting on that combined input, and finally output. And the diagram shows this as a perfectly straight one-way arrow from top to bottom. Like you said, no steps looping back, no memory connections to previous turns.
That one-way path is absolutely fundamental to the star model. It visually reinforces the defining characteristic. The interaction starts fresh, moves sequentially through these defined steps, delivers a single output, and then it concludes. Done.
Hmm.
There's no concept of continuing a conversation or remembering anything from before the specific turn began. And here's where it gets really interesting, I think.
Ah,
Seeing this flow laid out so clearly makes it incredibly obvious why mastering the single pass is the essential first step. You understand the mechanics of one interaction before you even think about linking them together.
that visual really grounds the concept.
Yeah.
Definitely. Now, you mentioned the agent's functionality relies on three core components working together. We kind of touched on them in the flow, but let's break them down individually. The greeting, the user input, and the system prompt. Why is each one so crucial?
Right. The notes highlight this quite clearly. The effectiveness and the specific behavior of your star agent are really defined by these three pieces. If any one of them is unclear or poorly designed, the whole interaction can kind of break down or give you a bad result.
Okay, let's start with the greeting then. It sounds simple, just hello, but as we discussed, it seems like it's more than just a welcome mat.
Much more, yeah. While it is the first point of contact, its primary purpose is functional, really. It sets the stage, it provides necessary context, and most importantly, it guides the user.
Guides them.
Yeah, think of it as the agent establishing the contract for this interaction. It's telling the user, look, this is what I'm designed to do, and this is the kind of information I need from you to do it effectively.
Oh, okay.
So for that lesson plan generator example, the greeting might be very specific. Please provide the subject, grade level, topic, and desired duration for your lesson plan. For a summary agent, it might be, paste the text you want me to summarize here and maybe tell me the desired length.
So its role is to actively steer the user towards providing input that the agent is actually equipped to handle, to avoid confusion or bad input.
Precisely. Its goal is to make the user input as effective and relevant as possible for this specific agent. The notes make a direct and powerful point about the impact of the greeting. A clear greeting leads to clear user input. Makes sense, right?
Yeah.
But conversely, a vague or confusing greeting inevitably leads to confusing input. And if you send confusing input to the LLM, well, you'll almost certainly get a poor, irrelevant, or maybe even nonsensical output.
So the quality of the output is profoundly influenced right from the start by the clarity of the initial instruction given to the user in the greeting.
Absolutely. It's the agent's first, and maybe best, chance to ensure success for this turn. It sets the user up for success.
Ah, so the greeting isn't just polite boilerplate. It's actually a critical piece of the prompt engineering puzzle itself. It influences what the user provides, which in turn impacts what the LLM receives down the line.
Exactly. It's about designing the user side of the interaction effectively. Now, the second component, user input, is where the user actually provides that information or request, responding to the greeting.
This seems like maybe the most obvious part. The user touches their message or clicks a button.
Well, yes and no. While free-form text input is very common and powerful, just letting the user type whatever they need, the notes point out that user input isn't limited to just open text boxes.
Ooh.
Depending on the specific function of the star agent, the input might need to be more structured. For example, you might use radio buttons if you need the user to select only one option from a predefined list.
Okay, like selecting beginner, intermediate, or advanced for difficulty.
Exactly. Or you might use checkboxes if they need to select one or more options, like choosing which sections to include in a generated report.
Why bother with structured inputs like buttons or checkboxes instead of just letting the user type freely? What's the benefit?
Because ensuring the agent receives the necessary information in a clean, unambiguous, and crucially predictable format is absolutely key to reliable processing.
Predictability again.
Yeah. If your agent is supposed to generate a quiz based on a topic, you could ask the user to type the topic. But what if they misspell it? Or use a slightly different term? If you want to make sure the topic is always chosen from a specific list of approved subjects that your system prompt knows how to handle, providing radio buttons prevents those typos or variations.
Gotcha.
Structured inputs reduce variability and improve the likelihood of a successful outcome for that turn. It's about making the gathering step of the algorithm as clean and error-proof as possible.
Okay, that makes sense. So the greeting prepares the user to give good input, and user input is where they provide it, possibly in structured ways for clarity. That brings us to the third component, the system prompt. This is the piece hidden from the user, the internal intelligence, the brain you mentioned earlier.
This is arguably the most crucial piece from the developer's perspective. It's the true brain or the operational instructions for the single-turn agent. The system prompt provides the underlying directives, constraints, conditions. Basically, it tells the LLM how to interpret and process the combined input it receives.
Which includes the user input.
Right, which includes the user input for that turn, and it also tells the LLM how to formulate the final response.
So if the greeting is telling the user what to do, the system prompt is telling the LLM what to do with what the user provides. Is that a fair way to put it?
Exactly. It's the developer embedding their specific logic and intent directly into the instruction set for the LLM for this particular agent's function. Its goal is to take the user's input for this turn, analyze it according to these internal instructions, and determine the precise action the LLM should take or the specific nature of the output it should generate. The notes give examples of the kinds of functions the system prompt can define. It could instruct the LLM to identify specific keywords in the user's text, or maybe apply particular logic like sorting or filtering. It could even define that the LLM should generate text in a specific persona.
Like act as a helpful history tutor.
Exactly. Or generate output in a particular format, like Markdown or JSON or a specific report structure. All of that is defined in the system prompt.
Okay, so putting it all together, greeting guides the user input. User input provides the specific data for the turn. And the system prompt provides the internal intelligence, the rules, the persona, the format, the logic that the LLM uses to process that input and generate the output. These three components, working together in that linear flow, define the entire behavior of the star agent for that single turn.
Precisely. And understanding how they interact, how they fit together, is really key to building any effective agent, even simple ones.
Let's circle back to that flow one more time now that we've detailed the components. The notes use a nice 3-act structure metaphor to summarize the interaction, which I found quite helpful for putting it all together.
Yeah, it's a helpful way to visualize the sequence. So, Act 1 is setting the stage. This is where the greeting takes center stage, really, and guides the user input.
Okay.
By crafting a clear greeting, the agent effectively defines the problem space for the user. It tells them the boundaries of what this agent is for and what kind of information is relevant or needed. This proactive guidance is crucial because it directly shapes the user input that follows. In essence, the agent tells the user what it needs to perform its task successfully.
Right. Act 1. The agent establishes the requirements for a successful interaction by managing the user's expectations and input.
Then comes Act 2, the fusion. This is that internal processing step where the system prompt and the user prompt are combined. The notes highlight the simple but powerful formula here. Input to LLM, system prompt plus user input.
The fusion moment.
Yeah. The system prompt is relatively static for a given agent. It's the core definition, the agent's personality or role. The user input is dynamic, changing with every single turn. Combining them creates a unique, specific instruction package for the LLM for that particular moment. It's not just giving the LLM some random user text. It's giving it user text within the explicit context and instructions provided by the system prompt.
So the LLM receives a task that is, like, predefined by the agent's overall purpose from the system prompt, but customized by the user's specific request in that turn from the user input. The system prompt is the how to interpret an act layer applied to the user input.
Exactly. It's the difference between asking a general AI, what is the capital of France, and asking an agent with a system prompts like, you are a quiz generator, use the following user input as a question and provide the answer only. The fusion creates the specific, targeted directive for the LLM.
Makes sense. And then Act 3, resolution.
This is where the result generated by the LLM, based on that fused input, is delivered back as the final output. The LLM has processed the complete instruction, leveraged its training data and capabilities, and produced a response that directly addresses the task defined by that combination of system prompt and user input. The formula is straightforward again. Result of LLM output to user. The agent has successfully processed the guided input and delivered the guided output. The turn is complete.
It's a complete cycle for one interaction. Finished.
Yes. And the notes summarize this underlying process quite nicely as the guide, gather, process, respond algorithm.
Guide, gather, process, respond.
Right. The greeting guides the user. The user input interface gathers the specific data. The system prompt combined with the LLM processes that gather data according to the defined rules. And the LLM result responds with the final output. This simple but robust algorithmic approach is powerful precisely because of its clarity and simplicity. It allows you to break down potentially complex problems into these single, manageable turns, making it possible to efficiently build what the notes call a vast number of useful single-purpose applications. Each application is just a specific implementation of this guide, gather, process, respond loop.
A vast number of single-purpose applications that really highlights the potential versatility even within this seemingly simple structure. The notes include a table with practical examples, right? Showing how the STAR model can be applied across different domains.
Yeah, that table is fantastic because it visually demonstrates how simply changing the content of the greeting and the system prompt fundamentally changes the function of the agent, while the underlying STAR structure, that guide, gather, process, respond thing, remains exactly the same.
Let's walk through maybe one or two examples from that table to see this in action. There's a lesson plan generator. How does the STAR structure create that?
Okay, simple application of the algorithm. The greeting is crafted to solicit the necessary information. Something like, enter the course subject, grade level, topic, duration, and any specific learning objectives. This guides the user clearly.
Yeah.
The user input is where you provide those specific details, maybe high school history, grade 10, World War II, 50 minutes, focusing on causes. The system prompt contains the core instruction for the LLM. You are an expert lesson plan generator. Based on the user's input, subject, grade, topic, duration, objectives, create a detailed step-by-step lesson plan suitable for a teacher to use. Include estimated timings for each activity.
Okay.
The LLM processes the fused input, the rules, plus the specifics, and generates the lesson plan as the output. It's a direct mapping of guide, gather, process, respond. Simple.
Okay, that makes sense. Very clear. What about something a bit different, like a grading assistant? How'd that work?
Sure. Here, the greeting focuses on receiving the student's work. Maybe, welcome to the grading assistant. Please provide the student's submission, like the text or a link to a document, and the grading criteria if you have them. This guides the user on the type of input needed. The user input is the actual submission text or link. The system prompt is where the grading logic is embedded. You are a helpful grading assistant. You will be provided with a student's submission. Analyze the submission based on the provided or maybe implied grading criteria. Generate a detailed grading report highlighting strengths, weaknesses, and suggesting areas for improvement. Provide a provisional score if possible.
Okay.
The LLM processes the submission according to these grading instructions defined in the system prompt, and the output is that detailed grading report.
That really illustrates how the processing step is entirely defined by the system prompt's instructions. It tells the MLM how to analyze the input, what rules to apply. Let's maybe look at one more, the medical scenario generator. That sounds interesting.
Yeah, this is a good example of potentially using more structured input like we talked about. The greeting might be something like, welcome to the medical scenario generator. Please select the type of medical emergency you'd like a scenario for from the list below, and maybe specify patient age and gender.
So using drop-downs or buttons?
Exactly. The user input here is likely a selection from a drop-down or radio buttons, for example, selecting cardiac arrest, and perhaps entering age and gender in separate fields. Then, the system prompt is tailored specifically to the medical domain. You are a medical simulation assistant. Generate a realistic medical emergency scenario based on the user's selected emergency type, age, and gender. Include patient presentation, vital signs, brief history, and environmental context suitable for training medical professionals.
Got it.
The LLM receives the structured selection and the age gender, processes it based on the system prompt's directive to create a medical scenario, and outputs the detailed scenario.
Okay, I'm really seeing the pattern now. The underlying structure, greeting, user input, system prompt, LLM, output, it's constant. But the specific content within the greeting, and especially the system prompt, completely dictates the agent's function, whether it's generating a lesson plan, grading work, creating a medical scenario, drafting an email, summarizing text.
Generating quiz questions, providing feedback.
Right. The notes mention examples across education, content creation, data analysis, medical fields, and probably loads more. The range is vast because, yeah, when you break down many tasks, they are fundamentally single-turn. Provide a specific input, get a specific output based on some fixed rules.
Exactly. You can conceptualize and build dozens, maybe even hundreds of these highly specific, useful STAR agents relatively easily once you grasp the pattern.
Okay, so you could end up with this big collection of many individual specialized tools. But the notes then introduce an advanced concept, which makes sense. How do you manage potentially a vast number of these useful single-turn agents? Building them all as separate standalone applications seems, well, inefficient.
That's precisely the challenge, isn't it? And it's where the true power of the star model's inherent modularity really comes into play. Building a separate web page or a separate script or a separate little app for every single turn function. Yeah, that becomes incredibly difficult to manage as the number grows.
I can imagine.
For the developer, maintenance is a nightmare. For the user, having like 50 different buttons or links for slightly different tasks is just overwhelming and confusing. So the solution presented in the notes leverages Star's modularity to handle many of these single-turn applications efficiently within one single application or platform.
Ah, okay. So instead of building 50 different tiny apps, you build one smart app that can be any of those 50 different tools on demand, depending on what the user chooses.
Precisely. This approach is dramatically more efficient for development. Adding a new single-turn function might be as simple as defining its greeting and system prompt and just adding it to a central list somewhere. For the user, it's a much more streamlined, unified experience. You open one application and it presents you with a menu of capabilities. It effectively creates a central library or a unified platform built from these individual, self-contained star components.
That sounds powerful. But how does one application dynamically switch between acting like a lesson plan generator one moment and a grading assistant the next? Especially since they use completely different greetings and system prompts.
Yeah, the core idea is parameterization, as the notes explain it. You don't hard code the specific text of the greeting and system prompt into the main application's logic for each individual function. Instead, you treat them as parameters that are stored centrally.
Centrally, like where?
Well, maybe in a configuration file or a simple data structure like a list or dictionary or even a database, depending on the scale. The notes use this at symbol convention, you might have seen, to represent these parameterized fields like @greeting or @system prompt @b. These are basically placeholders that get filled in dynamically when needed.
So the app knows about all the possible greetings and system prompts it could potentially use, but they're stored outside the main flow ready to be fetched.
Correct. The app has access to, let's call it, an agent library or a list of available agents. And each entry in this library conceptually holds the specific @greeting @text and the specific @system prompt @text required for that particular agent, along with its name or title.
Right.
So the quiz generator entry in the library has its specific quiz @greeting and its specific quiz @system prompt @meeting, while the feedback generator entry has its own specific feedback @greeting and @system prompt @lean and so on for all the agents the app supports.
Okay, I think I'm following. It's like having a menu and a big recipe book. The app knows the names of all the dishes on the menu, and it knows where to find their recipes in the book, but it doesn't have all the recipes open and active at the same time.
That's a great analogy. Exactly. And this structure leads directly to the dynamic user flow within the single app, which is essentially a two-step process managed by the core application logic.
Okay, what's step one?
Step one is agent selection. The application starts with a master greeting that's generic to the platform itself. Something like, "Welcome, please select the AI agent you'd like to use today." It then presents you, the user, with a list of all the available single-turn agents it knows about, maybe as a drop-down menu or a grid of buttons or a list of cards, whatever the UI is. You then choose the specific function you need right now. Let's stick with our grading assistant example. You click on Grading Assistant.
So the very first interaction isn't actually a star turn itself, but it's an interaction to choose which star agent you want for the next interaction, kind of a meta step.
Precisely. Your selection in this first step is crucial because it tells the application which specific set of star components, the correct greeting, and the correct system prompt it needs to retrieve and activate for the subsequent steps.
Okay, so I've selected Grading Assistant. What happens next? That's step two.
Step two is the actual star execution. Once you've selected Grading Assistant, the application acts as the orchestrator. It dynamically retrieves the specific @greeting associated with the Grading Assistant from its central library, its recipe book, and it displays only that greeting to you.
Ah, I see. So the initial menu disappears, and now the screen shows the greeting specific to the Grading Assistant. Welcome to the Grading Assistant. Please provide the student's submission, or whatever it was.
Exactly. The app has effectively loaded the correct personality and instructions for this specific star agent. It then waits for your user input for that specific greeting, just as a standalone star agent would.
And when I provide the input, say, I paste in the student's essay, what does the app do then?
The application then dynamically retrieves the corresponding system prompt from the library again, the one linked to the grading assistant selection you made right at the start. It programmatically combines this retrieved system prompt with the user input you just provided, the essay. This correctly assembled, tailored prompt, the grading assistant system prompt, plus the student essay input, is then sent off to the underlying LLM for processing.
And the LLM processes that complete instruction package, which is specifically formatted for grading because it got the right system prompt, and delivers the grading report as the output.
Correct. The key insight here is that it's still fundamentally a single star turn happening. Input, your essay, process LLM with the correct grading system prompt, output, the grading report. But the specific parameters, the greeting and the system prompt that defined how that star turn functions were dynamically chosen on the fly based on your initial selection from the menu.
This is what's fascinating here. It really is one application housing potentially many distinct star agents.
Yeah.
And it uses the user's first action, selecting from that menu, to configure itself for the second action, which is executing the specific star function they wanted. It feels like many tools, but it's built on a really clever, modular architecture using that fundamental star pattern.
Absolutely. It leverages the reliability and simplicity of the basic star model for each individual function, but wraps it in a structure that provides the efficiency, scalability, and user-friendliness of a single unified application. It turns what could be a messy collection of single-purpose tools into a genuinely versatile platform.
That setup makes conceptual sense, definitely. But how does the application actually know, like under the hood, which specific greeting and system prompt belong to which agent name when the user makes their selection? What's the underlying code logic that enables this dynamic retrieval you're talking about?
Yeah, good question. The notes provide insight into a common and pretty effective way to structure this using a simple but powerful pattern based on parallel lists of parameters. Think of it like having three separate lists stored in the application's configuration or code, where the order within each list is absolutely critical.
Three lists.
Yeah.
And they're linked somehow by their position, like item #1 in list A matches item #1 in list B.
Precisely. The first list holds the names or titles of all your available agents. Let's call it agent title. It might look something like lesson plan generator, quiz generator, grading assistant, medical scenario generator. The items are separated somehow, maybe by a pipe symbol as shown in some examples, or just stored as elements in a list data structure.
Okay, so that's the text that appears on the menu for the user to choose
Yeah,
from.
right. Now the second list is greeting. This list contains the specific greeting text for each agent, and the crucial part is that the greeting for lesson plan generator must be in the exact same position, the same index in the greeting list as lesson plan generator is in the agent title list.
So if lesson plan generator is the first item, index 0, its greeting is also the first item, index 0 in the greeting list.
Exactly. And if quiz generator is the second item, index 1 in agent title, its specific greeting is the second item, index 1 in the greeting list, and so on.
And I'm guessing the third list is system prompt.
You got it. This list holds the specific system prompt text for each agent, again, maintaining that exact same parallel order. The system prompt for quiz generator is also at index 1 in the system prompt list. The link between the agent's name, its greeting, and its system prompt is their shared position, the numerical index, across these parallel lists.
Got it. The index number is the key that ties them all together.
Exactly. The index is the magic key. Now, let's look at the execution flow using those example prompt syntaxes from the notes, which show how the application might use this structure.
Okay, the first prompt syntax shown is something with @select. What's that doing?
Yes, that's used for the initial agent selection step. Step 1. The syntax provided looks like select S1, select AI agent, at agent title, at day. Let's break this down. Select at is basically a command telling the application, hey, create a selection interface for the user. S1 looks like a variable name where the application will store the result of whatever the user selects. Select AI agent is the static text prompt displayed to the user, the master greeting for the selection menu itself. And at agent title at agent is the placeholder that tells the application, go get the contents of the agent title list and use those items to populate the selection interface, like the options in a drop-down menu.
Okay. So this one line of code essentially creates the menu, labels it, select AI agent, fills it with the names from the agent title list, and then waits for the user to pick one. And whatever the user picks, so they click on grading assistant, that text grading assistant gets stored in the S1 variable.
That's precisely what it does. And that value stored in S1 is the key that unlocks the rest of the process for this turn. So the next step in the flow is displaying the greeting specific to the agent they just selected. The prompt syntax shown for this is at greeting, at index, at agent title, at AVA, at select S1, at A of V, at AF.
Whoa, okay. That looks a bit complex. At greeting and at index.
It might look a bit complex initially, yeah, but the most important part inside those square brackets is the at index function.
And at index. Finding the position, the index number.
Exactly. At index, at agent title, at YIBO, at select S1 at S1 tells the application, go to the agent title list. Find the text that was selected by the user and stored in the S1 variable. In our ongoing example, that's the text grading assistant. Tell me the numerical position, the index of that item within the agent title list. Remember, computer lists usually start counting at 0. So if grading assistant was, say, the third item in the agent title list, at index would return the number 2.
Okay, so it translates the user's selected name, grading assistant, into a specific number, like 2, representing its position in the title list.
Exactly. And then the outer part, at greeting, uses that index number. It tells the application, now go to the greeting list and retrieve the text that is located at that same index number. Index 2 in our example. Since the lists are perfectly parallel, the item at index 2 in the greeting list is the specific greeting for the grading assistant.
This raises an important question. How does it know which greeting to show? Through the index. Okay, I get it now.
Right.
It finds the selected agent's position in the title list and uses that same position number to grab the matching greeting from the greeting list. That's actually a really elegant way to link them dynamically without hard-coding everything.
It is elegant and very efficient. It's a core pattern you see a lot in software development, using an index or a key to look up related information in parallel data structures or tables. And as you might guess, the logic for applying the correct system prompt for the LLM is built on this exact same pattern. The notes show something like, system part of the prompt, set to at system prompt, at index, at agent title, at all capat, at select S1, at alt capat.
Okay, so it uses the same at index function, still based on the user's initial selections stored in S1.
Precisely. It calculates that same index number that corresponds to grading assistant in the agent title list, which was 2 in our example, and it uses that same index 2 to pull the correct system prompt text from the system prompt list.
And that specific system prompt text, the one retrieved using the index corresponding to the user's original selection, is the one that gets combined with whatever the user types next, their actual request for the grading assistant like the essay, to form the complete, tailored instructions sent to the LLM for this single turn.
That's it. The entire dynamic system hinges on that initial user selection generating an index, and then consistently using that single index number as the key to retrieve the correct components the greeting shown to the user, and the system prompt used internally by the LLM from those parallel lists. This is what allows one application to seemingly behave like many specialized star agents, dynamically loading the correct configuration for each interaction based purely on the user's choice. It's a powerful architectural pattern for building modular and easily expandable AI applications.
That breakdown of the logic makes it much clearer how a single app can be so versatile. It's essentially performing a lookup, like in a database, based on the user's selection to grab the right set of instructions for the LLM for that specific turn. Really neat.
It is, yeah. And this entire exploration, from the simple single turn of the basic star model all the way to this dynamic selection mechanism, it really circles back to the core principle the notes emphasize repeatedly. Developing generative AI agents, regardless of how complex they seem, is fundamentally about modeling the task and applying algorithmic thinking.
Modeling the problem, breaking it down into steps, and thinking algorithmically about the sequence, the inputs, the output.
Exactly. Every agent, from the simplest star to the most complex multi-agent system you can imagine, ultimately follows variations of that fundamental structure. Input, process, output. To effectively model a problem for an AI agent means asking those basic questions. What information do I need to take in? That's your input. What specific steps, rules, or transformations need to happen to that information internally? That's your process, often involving the system prompt. And what is the desired final result or action that should be produced out? That's your output. The STAR model, as the notes correctly identify, is the purest expression of this input-process-output principle. It forces you, the builder, to define the smallest possible self-contained unit of useful interaction first.
So for someone listening who wants to move from just understanding this, actually building something, where's the best place to start applying this STAR concept? How do they find their first STAR project?
The practical advice offered in the notes is excellent, I think, because it makes it immediately relatable. It says, look at your own life, your work, your daily routines. Identify those small manual tasks you find yourself doing repeatedly.
Repetitive tasks. Like what?
Well, do you often write similar types of emails, maybe changing only a few key details each time? Do you regularly need to generate draft content for social media or blog posts that follows a consistent structure? Do you find yourself creating checklists or meeting outlines based on a specific input or topic? Each of those small, repetitive tasks is a potential candidate for a simple star agent.
Ah, so you provide the variable info, the names, the topic, the date, and the star agent generates the standard output, like the email draft or the checklist, tailored by those variables. It's like a
Okay.
dynamic template filler.
Precisely. It's exactly like a dynamic template. And by starting small, by attempting to build a simple star agent, maybe just a few lines of code using an LLM API, or perhaps using one of the many visual building tools available now to automate or just assist with one of these small, repeatable tasks, you gain what the notes call invaluable hands-on experience in a low-risk environment.
Right.
You don't need to try to build a chatbot that can discuss philosophy right away. You can build a simple tool that helps you draft meeting agendas faster or summarize articles you've bookmarked. Start simple.
And this practice of building simple stars, that's where you truly learn the nuances of working with the LLMs themselves,
Yeah.
right? It's not just about the structure.
Crucially, yes, that's a key point. While the single-turn agent is limited by definition, it lacks memory across turns, it can't handle complex back-and-forth conversations, it's not really suitable for tasks requiring ongoing statefulness. It is an incredibly powerful training ground for understanding the LLM itself.
So
Building star agents forces you to get good at prompt engineering. How do you phrase the system prompt and guide the user input to get the desired, reliable output from the LLM? You learn the importance of providing sufficient context within that single turn, because that's all you've got. You begin to understand the LLM's capabilities, what it's good at generating or analyzing, and just as importantly, its limitations and how its responses can sometimes vary or be unpredictable.
it's like learning the basic controls, the throttle, the steering, the brakes, on a simple vehicle before you try to pilot something much more complex, like a plane.
Mm.
You have to master the fundamental interactions with the machine first.
That's a perfect analogy, exactly. Mastering these basic controls and understanding how input, process, and output work together via the greeting and the system prompt builds the essential foundational knowledge. And if we connect this back to the bigger picture, the roadmap ahead, this understanding of STAR is the non-negotiable first step towards grasping more advanced concepts. It's absolutely necessary for understanding multi-turn systems, which manage conversation history often by cleverly linking multiple star-like interactions together while carrying context forward from one turn to the next. And it's essential for understanding multi-agent systems, where different specialized agents, each potentially a star agent or a sequence of stars, collaborate and pass information between each other to solve more complex problems.
So you have to understand the individual units, the stars, before you can understand how networks or sequences of those units function together.
You really do. STAR is the entry point. It's definitely not the final destination of AI agent development, but it's the gate you absolutely must pass through to get there effectively.
It seems like STAR is the key to unlocking that initial complexity.
Precisely. It distills the potentially overwhelming complexity of building with generative AI down to a manageable, understandable, and crucially buildable unit, the Single-Turn Agent Replicator.
This deep dive into the STAR model, based on these lecture notes, it really does provide a clear pathway into AI agent development. It helps demystify that initial feeling of overwhelm by giving you a concrete foundational concept and a practical starting point.
Yeah, it frames the challenge not as mastering some inscrutable AI magic, but rather as applying fundamental modeling principles and algorithmic thinking to leverage a very powerful new tool.
So, recapping the core idea, the STAR model is the fundamental building block, the pure input process output core for creating generative AI agents. Mastering this simple structure and understanding how the greeting, user input, and system prompt work together to define its function is the essential first step towards building any kind of AI agent, no matter how complex your future projects might become.
Absolutely. It provides the necessary hands-on experience with prompt engineering, with managing context within a single turn, and just generally interacting with an LLM in a controlled, predictable environment.
So thinking about all we've discussed today, identifying those small, repeatable tasks in your own life or work, seeing how they could maybe be broken down into that simple guide, gather, process, respond algorithm, and understanding how the greeting, user input, and system prompt combine to make that happen. Well, what stands out to you listening right now? Can you start to spot opportunities for creating simple, single-turn agents in your own daily routine? Think about all the places where you provide one piece of information and get one specific result back. that specific interaction might just be your first star agent waiting to be built.
Or even just looking at the apps you already use every day. Can you start to recognize moments where you're likely interacting with a single-turn system? Maybe selecting an option from a menu, filling out a short form, providing one specific input to get a tailored output back. Understanding the star model helps you see the underlying mechanics potentially everywhere, even in tools you thought were much more complex. It's a lens for seeing simplicity.
That's a great way to start applying this knowledge and recognizing the pattern in the world around you. Well, thanks for joining us for this deep dive into the foundational star model.
Always a pleasure. It's a fascinating starting point.